So this is about Rutherford's gold foil experiment as it is in the A-level syllabus, particularly the final chapter of the AS syllabus, which is about radioactivity. So first of all, the definition of radioactivity is that it is the process whereby unstable nuclei emit radiation. And unstable nuclei emit it so that they can kind of stabilize themselves and make them a bit more less radioactive. And they also sometimes emit radiation because they have excess energy and they emit radiation in the form of gamma rays, which are photons. So this is Rutherford's gold foil experiment, which basically helped to kind of present a model for the atom that we know and learn about today. So over here, he has this setup, and we can see that there is a source of alpha particles right here, and that is where the alpha particles were emitted in a straight line towards a gold foil, and this was extremely thin. It passed through it to hit the scintillating material, which was just right here, and then the microscope was behind it, which helped us to kind of look at it closer and detect it better. The whole entire setup was actually in vacuum, and there was absolutely no air inside it, and therefore we had this like little leading up to vacuum pump as well. So why the setup was the way it was? First of all, the microscope can be moved around to detect alpha particles at different angles. The whole point of this experiment was to find out whether or not the path of the alpha particles were somehow affected by the gold foil. And by somehow affected, I mean their path was basically distorted from the straight line path to maybe put them off at an angle. Maybe they would make them go a curved path, for example. Maybe they would kind of bend the path when they hit the gold foil. So that's why it was really important that it could be moved around at angles. For example, it was set at an angle of 1 degree, and then we would count how many alpha particles were detected out of all of that was emitted. Secondly, the gold is used in specific terms gold because it can be made into a very thin sheet. It's very ductile, malleable, and this one in particular is 10 to the power of negative 6 meters thick, which is equivalent to 1 micrometer thick, and that's very, very, very thin. It's just hundreds of gold atoms thick, and in comparison, a strand of our hair usually contains 1 million carbon atoms. Admittedly, gold atoms are much bigger than carbon atoms, but to put that in perspective, this was an extremely thin sheet. At first, Rutherford did use mica sheets as well. All the particle sources are encased in a metal with a small aperture, and you can see that there's a tiny little like opening, and that's where the alpha particles come out of. So it's there so that only a small beam emerges out of the source. The rest of the metal casing will completely absorb the alpha particles that are emitted by the source. Even a sheet of paper can absorb alpha particles. So a casing of metal should completely absorb all of that is actually emitted, except for this tiny little hole. Air is also pumped out to leave a vacuum. And the reason why this is so important is because alpha particles are extremely ionizing, which means they will collide with whatever there is, and they will collide with particles in the air in this case. They're going to ionize them, and they're going to eventually lose their energy, which means that not all of the alpha particles will be detected by the microscope, and it won't be an accurate experiment. So in order to make sure that the alpha particles don't collide haphazardly, and then, in order to make the experiment into a more accurate one, there had to be a vacuum so that its path was cleared. And it's actually just absorbed by 5 to 6 cm of air, so it was really important that it didn't have this effect. This scintillating material right here is something that actually gives little bursts of light when it's hit by alpha particles, so that's how we detected it at first. His assistants used to sit in a dark room and count these little bursts of light one by one, and it was so straining for them to concentrate on something this hard that they had to constantly alternate it, and they couldn't even focus on it for a minute, or maybe more than a minute usually. So what this eventually led up to is he found out three things, and it could all be kind of like concluded into 3 points. First of all, most of the alpha particles experienced little to no deviation. If they did, it was like smaller than 1 degrees also. And so he concluded that most of the atom is empty space because most of the radiation that passed through it didn't really get acted on by anything. Very few of the alpha particles, and that's approximately 1 in 20,000, were deviated at an angle that was greater than 90 degrees. This means that if this was kind of the atom, and then that was the initial path of the alpha particles, if you were deviated like this, so that is an angle that is greater than 90 degrees, because this is 90 degrees and it's a much greater angle. The rest of them maybe had a small deviation like this, and that is a smaller angle than 90 degrees. So these cases were extremely rare, only 1 in 20,000. And therefore he concluded that most of the mass of an atom and all of the positive charge was concentrated in a small space, and most is empty. So we can get why it was a small space, but why is it all of the positive charge? Well, that's because the positive charge needs to be really concentrated to have that big of an effect on the path of an alpha particle. If the positive charge was not concentrated, then that means that it could not possibly have all of the force, the electrostatic repulsive force, to actually turn around an alpha particle in its tracks and make them deflect by that big of an angle. Therefore, for the intensity of this force to be really, really big, you had to concentrate it into an extremely small space. And small being that only 1 in 20,000 actually came close enough to this tiny little concentrated space to actually be affected by it. The third conclusion is that alpha particles were deflected due to the repulsive electrostatic or Coulomb force between the positive charge of the alpha particle and that of the gold nucleus. So the gold nucleus obviously has a positive charge because it's constituted of protons and neutrons, and therefore if you went close enough to it, it was deflected. Why it had to be that they were deflected by the nucleus and not like the electrons around it is that alpha particles are extremely huge in comparison to the electrons, and therefore the amount of force that would be between them would not be very substantial. They would have to collide with something that is much bigger than their own mass, and therefore electrons could not have that much of an effect. And it had to be something that was huge, that had so much charge that could actually knock an alpha particle out of its tracks, while electrons only have a very small charge of like 1.6 to the power of negative 19 coulombs. The positive charge in gold nuclei. So gold nuclei have 79 protons, which means it has 79 times the charge of an electron, but in a positive form, and therefore that was needed for it to actually make a dent in the rote of the alpha particle, and therefore electrons could not possibly be the source. And it had to be protons or positive forces that were making the change, and therefore he concluded that it had to be concentrated for it to actually make an impact. So before Rutherford actually did all of this, there was actually another kind of model in place, which was called the Plum pudding model, and this is kind of the Plum pudding model right here. As you can see, this kind of like green ball is what the positive forces were envisioned to be. They thought that it was kind of a positive ball with small little lumps of electrons studded on it, and this disproved it for 3 reasons. First of all, like the positive charge, it disproved it for 1 reason, which is that if the positive charge was so spread out in such a big volume, then that means the intensity of the electrostatic repulsive forces would be extremely small, and it would not nearly be enough to stop and change an alpha particle in its tracks. And as I already explained before, the electrons could not be the source of this like deviation of root of the alpha particle. And therefore, if the Plum pudding model was true, there should be no deviation at all, because they couldn't have the effect to change the alpha particle's root. They couldn't have that strong of a force. So they needed to be concentrated in order to have a bigger intensity. And therefore the Plum pudding model was disproved. His model was really, really easily and quickly accepted by the general scientific community, and that was because it also helped to explain a lot of chemical phenomena that atoms went through, and chemists did agree with this model because it helped to explain a lot of it. A head-on collision, which means they hit the atoms perpendicularly. So if this was the nuclei, they would hit it like at an angle of 90 degrees. So it's just straight on. This will mean that they will have a deflection of 180. So they would just completely go back like that. And that is a deflection from its usual path of 180 degrees. The gold nucleus, and that's AU actually, and alpha particles will experience equal and opposite forces, but there will be a much greater impact on the alpha particle, because the alpha particle is so much smaller than the gold nucleus. The gold nucleus has a nuclear number of 197, so altogether it has 197 protons and neutrons. An alpha particle is consisted of 4 nucleons, and that's basically just 2 neutrons and 2 protons. So in comparison, it's absolutely tiny, and therefore, by the law of momentum, its own path would be distorted way more than the nucleus of gold. So that is about it for the Rutherford's gold foil experiments that helped to make the model for atoms. And yeah.